Hello, dear students. Good evening and welcome to this episode of JEE Main revision classes of race. And today we will have the module 4 based on organic chemistry, some basic principles and techniques, and hydrocarbons. As you know, these two chapters are in the 11th standard. This is the 11th standard organic chemistry, and whatever you study in the 12th standard is a continuation of these basic organic chemistry and the chemistry of hydrocarbons. Now, being the basic chapters, it is very important that you go through even the minutest details about these two chapters, because that will help you a lot in understanding the topics in the second year program. So we have, as usual, 25 questions, 20 questions, multiple choice type questions, and 5 questions, the integer answer type questions. And the time allotted is 2 hours and 30 minutes. I don't know whether it will be completed in 2 hours 30 minutes. I will try my level best to discuss all the questions in the fullest length possible. Okay, let us start. Here is the first question. The question is about an alkyne. C6H5, C triple bond, CCH3. And what is written on the arrow? You may please go through what is written. It is sulfuric acid, mercuric sulfate. And this is a very known reaction. Sulfuric acid obviously will help the acid catalyzed hydration of the triple bond. It is equivalent to H plus H2O. You can write H2O, H plus, or H3O plus, or H2SO4. Whatever it is a proton catalyzed reaction, and you require a water molecule for fulfillment of the reaction. So it is reaction with the sulfuric acid in the presence of mercuric sulfate. The only role of mercuric sulfate in this reaction is the role of a catalyst. So the reaction is catalyzed by mercuric ions, Ag2 plus, and the reaction is actually with the sulfuric acid, and the actual thing during the reaction is acid catalyzed hydration of the triple bond. That means just the addition of one molecule of water catalyzed by protons. And what happens in this addition of water? Addition of water will give you C double bond C, CH3, that is the substrate. So addition of water will give you HOH. This is a sort of addition. So what you get is COH double bond CH3, isn't it? C. Okay, this is what you get, COH, and there is a double bond. There is a double bond here, okay? Double bond. And here it is CH. And look at the molecule. So let us continue. So adding a molecule of water catalyzed by protons, the product obtained would be C6H5COH, double bond CH, CH3. Okay? But look at this molecule very carefully. You will see that this is an enol. A double bond COH structure is what you call an enol, E-N-O-L, enol. And you have seen that such enol molecules can rearrange by a hydrogen shift and a pi electron shift. A pi electron shift like this towards CO and a hydrogen shift like this. What you generally refer to as tautomerism. So this molecule actually tautomerizes into a more stable compound CO, CH2, CH3. CH2, CH3. That's the compound that is formed. So it's a ketone that you get. And obviously the answer is C6H5, CO, CH2, CH3. CO, CH2, CH3, that is the answer A. A is the answer. A is the answer. You must remember that such questions are very common in JEE main question papers. You may get questions based on acetylene, in which case on adding water you will be getting vinyl alcohol, and this vinyl alcohol undergoes a rearrangement of this sort and the product would be acetaldehyde. And suppose it is methyl acetylene CH3C triple bond CH. A similar addition of water molecule followed by tautomerization will give the compound CH3COCH3. And suppose the starting compound is a compound like C triple bond CH. In that case, the product that you get will be acetophenone, COCH3. All these reactions are of the same type. Acetylene into acetaldehyde, or propyne into acetone, or this compound phenylacetylene into acetophenone, or the given conversion. All these reactions basically are the same type of conversions, where it is acid catalyzed hydration to a triple bond forming an enol which undergoes tautomerization to give a ketone, and you get an aldehyde only in the case of acetylene. In the case of acetylene you get acetaldehyde. In the case of all other compounds you will get a ketone, and that in fact is one of the methods very often used for the preparation of ketones. That's an important reaction, and question of this type very often asked in JEE main question paper or even in advanced question paper. Now coming to question number 2, please read the question. 2-methyl-butane on reacting with bromine in the presence of sunlight gives mainly. Bromine in the presence of sunlight means a photochemical reaction, and bromine in the presence of sunlight means bromine dissociates by the homolytic fission forming the bromine radicals. So obviously the reaction is a radical initiated reaction. In the presence of sunlight it's a radical initiated reaction. So you have 2-methyl-butane. 2-methyl-butane is this one, CH3, CH2, CH, CH3, CH3, that is 2-methyl-butane. And when it forms a radical, when a bromine radical attacks this molecule, the bromine radical will take a hydrogen forming a radical on the hydrocarbon chain. And what will be the radical on the hydrocarbon chain? If this hydrogen is detached, you will get a primary radical. If this hydrogen is detached, you will get a tertiary radical. And if this hydrogen is detached, you get a secondary radical. And if this hydrogen is detached, you get a primary radical. And you know the stability of radicals, tertiary greater than secondary greater than primary. So obviously, it is this hydrogen, the hydrogen on the second carbon, which is replaced by bromine, or which is detached to form that radical, C radical, and the bromine will be attached at this carbon, and therefore the product of the reaction will be 2-methyl, 2-bromo, 2-methyl-butane. 2-bromo-2-methylbutane. That is, the answer is A. A is the answer for this reaction. I hope you understand what is the underlying principle. It is the stability of free radicals. A tertiary free radical is more stable than secondary, more stable than primary, and the radical obtained by removing the hydrogen from the second carbon atom is a tertiary radical, and obviously that is the most stable, and therefore the reaction will always like to follow that pathway of the reaction of the tertiary radical with Br dot. With the Br dot, what you get is CH3, CH2, CCH3, okay, BrCH3. That's the compound 2-bromo-2-methylbutane. So that is answer A. So what is important is, in the presence of sunlight, remember the reaction is photochemical, and photochemical reactions generally follow free radical mechanism. So the bromine molecule dissociates given the bromine radicals, and the bromine radical attacks the hydrocarbon substrate and will take a hydrogen, generating a radical on the hydrocarbon chain, and see the stability of the radical. Keep in mind the stability of the radical. If it is a tertiary radical, okay, well and good. The tertiary radical will react with the Br dot, forming the desired product. Suppose it is not a tertiary radical, in another case, so for example, some other hydrocarbon is given, and suppose you find that the radical is not a tertiary radical, think of the possibility of rearrangement into a tertiary radical. If a tertiary radical is obtainable by rearrangement, then obviously the tertiary radical will be formed, and the product would be one corresponding to the tertiary free radical. So that is the essence of the question. I think the question is pretty easy. Everybody can answer that question. Okay, we will move to the next question. So this is the question. You have an aromatic hydrocarbon. Don't be afraid of the side chain. The side chain contains 3 carbon atoms. That's okay. So it's a 3 carbon atom side chain, CH2, CH2, CH3. And this also is a 3 carbon atom side chain, CH2, CH2, CH3. And the reagent is alkaline potassium permanganate. And once you hear alkaline potassium permanganate, remember the reaction. What is the reaction? Side chain oxidation. That means the side chain, irrespective of the length, whether it is a 1 carbon chain or a 2 carbon chain or a 3 carbon chain, the chain is ultimately oxidized into a carboxyl group, provided you provide enough amount of alkaline potassium permanganate. So what is given in the question is alkaline permanganate excess. That means you have enough of the reagent so that the complete oxidation of the side chain to the acid group is possible. So what you get in the reaction is this one. What you get is the phthalic acid. These 2 side chains getting oxidized to COH group. So it is phthalic acid that is formed. Okay. So that is the product A. A is phthalic acid, right? And the next reaction is to react with ammonia. Normally, when a carboxyl group reacts with ammonia, the product formed in the reaction is ammonium salt of the acid, which decomposes to form the corresponding amide. Amide means CONH2. But in this case, it is a dicarboxylic acid where the acid groups are at ortho positions very close to one another, so that on reaction with ammonia, the amide will be initially formed, and then it will be forming the imide, NHCO. The NH between 2 CO groups is what you call imide. I think you are reminded of the compound thylamide, and this is thylamide. What is formed here is the imide of phthalic acid. The imide of phthalic acid is known as thylamide. And once you hear thylamide, you are reminded of the reaction Gabriel's thylamide synthesis. It is exactly what is given in this question, Gabriel's thylamide synthesis. So this is the compound B. This is the compound B. On reaction with ammonia and strong heating, you are getting the imide as the product. And now the imide B is treated with the KOH. On reaction with the KOH, what will happen? Remember that this NH group, on either sides of which you have the electron withdrawing carbonyl groups, such imide structures, the hydrogen on the imide structure has acidic property. The imide is acidic. The hydrogen on the nitrogen atom is acidic. And therefore, on reaction with a strong base like KOH, it can give this corresponding salt. So what is formed is the salt of phthalimide, N minus K plus. Okay? And this salt, phthalimide salt, will easily react with an alkyl halide, RH, and you will get the alkyl phthalimide, which on hydrolysis will form the primary amine. But here in the question, the symbol alkyl halide is not given, but what is given is the alkyl halide, which also contains a acid group, COOH. But that doesn't matter. There is a chlorine atom on the carbon, and it is that part of the molecule which actually combines with the phthalimide. Actually, it is an SN reaction. The phthalimide ion will act as a nucleophile. The phthalimide ion is replacing the chlorine atom in the compound, and therefore you get the product. You get this product, CO, N, okay, there, CH, that CH3 is there, and COOH. It is this group, the phthalimide group, the phthalimide ion. The phthalimide ion acts as a nucleophile. Remember, it's a SN reaction there. The phthalimide ion now reacts with the alkyl halide part of the molecule, CH3CHCl-COOH, that is alpha chloropropanoic acid. The CCl bond, that is the bond, reactive site with this particular nucleophile. The chlorine is replaced by the nucleophile, and you are getting this compound. And this compound, that is the compound C. This is the compound C, and this compound on hydrolysis gives P, Q, and R. This compound on hydrolysis, here there will be cleavage. You have HOH, and here also you have HOH. That means the phthalic acid is formed in the final step as a product, okay, plus this part is NH2 group. You have NH2 CH3 COH. Okay, so that is the whole sequence of reactions. I repeat, you have the phthalic acid as an oxidation product. Okay, both the propyl side chains are completely oxidized to the acid group, and once the phthalic acid reacts with ammonia, you have the phthalimide as a product, and the phthalimide, by virtue of the NH group between two carbonyl groups, has acidic property at the NH group. The hydrogen atom there is acidic, and on reaction with the KOH, you have the potassium salt of phthalimide, potassiothalimide, and the potassiothalimide reacts with an alkyl halide. In this case, the alkyl halide is alpha chloro or 2-chloropropanoic acid, and the alkyl halide part reacts with this nucleophile, okay, or the conversely, the phthalimide nucleophile reacts with the alkyl halide, part of the alpha chloropropanoic acid, to give this compound. And this compound on hydrolysis, that is the last step. Actually, on the arrow mark, one has to give H2O, H plus, hydrolysis, and you get phthalic acid. Again, the ring is opened, and you have phthalic acid and the corresponding primary amine. The Cl is replaced by NH2. So what you get is CH3CHNH2COOH. Okay. So which statements are incorrect regarding the final products P, Q, and R? And actually, R is nothing but KCl. KCl is the third compound. This is the first compound, this is the second compound, and this is the third compound. The third compound is just a potassium chloride. That's all. So the major products of the reaction are phthalic acid, and what is given as product B there, CH3CHNH2COOH. It's an amino acid, alpha aminopropanoic acid. That is the second product, and ETOH is not a product. We are not seeing ETOH on any place here in the reaction sequence. So ETOH is not a product of the reaction, and the pure amine CH3CHNH2COOH, that also is not a product. What is formed is amino acid, and amino acid is fairly stable. It doesn't easily undergo decarboxylation, and therefore the product 2-aminopropane, that is very unlikely. So the product ETOH is not a product, and CH3CHNH2 CH3, that is also not a product, and the products are phthalic acid. And so statement 1 is correct, statement 2 is correct, okay. Statement 3 is wrong, and statement 4 is wrong. So the wrong statements or the incorrect statements are C and D. C and D are the incorrect statements. A and B are the correct statements. So you must know the sequence area. That's the important thing. The Gabriel's phthalimide synthesis that has been utilized in this reaction sequence. And initially you have the chemistry of the aromatic hydrocarbon, that is the typical reaction, what you call the side chain oxidation, where the side chain in the aromatic ring is oxidized to a carboxyl group on reaction with alkaline potassium permanganate. And there you remember that irrespective of the size of the alkyl group, whether it is 1 carbon or 2 carbon or 3 carbon containing alkyl group, remember, if you provide enough of alkaline permanganate, then it is possible that the group is completely oxidized into an acid group. So that's why you get phthalic acid as a product. The phthalic acid on reaction with excess alkaline KMnO4. Of course, it may take long duration for the complete conversion to take place, but that's not immaterial. The final product of the reaction is phthalic acid. So A is phthalic acid, B is phthalimide, and C is the phthalimide reacting with this alpha chloropropanoic acid or 2-chloropropanoic acid, that product. And on hydrolysis, the last arrow mark must contain hydrolysis or H2H plus, that has to be given on the last arrow. On hydrolysis, you get phthalic acid and this compound 2-aminopropanoic acid. Okay, so A and B are the products, and C and D are not the products. So incorrect statements are C and D, and the correct statements are A and B. Okay. That is the next question. So next question is about a hydrocarbon C5H12. C5H12 corresponding to the formula CnH2n plus 2, you know, is a saturated, aliphatic saturated hydrocarbon. So when you read the question, immediately you can understand that it's about an aliphatic saturated hydrocarbon. That means a pentane. And pentane has isomeric structures, you know. Anyway, C is not an option because it contains a double bond and the formula doesn't suit that of a aliphatic saturated compound. So you can straight away rule out C. So of the 3 cases A, B and D, that's the question. Of the 3 cases, we can straight away rule out C. C is not an answer. And then it does not react with the chlorine in dark, but gives 6 monochloro compounds in bright sunlight. As we discussed with the question number 2, as a photochemical reaction, it is free radical chlorination. But here the question is not only the mechanism of the reaction, but how many products are obtainable. Which isomer will give 6 monochloro compounds? That is a question. 6 monochloro compounds. Which isomer among A, B and D of pentane, which isomer will give 6 monochloro compounds? So you can try. In the case of compound A is nothing but CH3, CH2, 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 CH3, the straight chain compound. Of course, it is given as a zigzag structure. That is actually the conventional way of write in the bond line structure. But when we translate into the usual way of representing the molecule, it is CH3, CH2, 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 CH3. Okay? And now do the monochlorination on this compound. You can do the chlorination here, or it can be clear, or it can be here. Right? So there are three possibilities. The monochlorination may be on CH3, maybe on CH2, or maybe on this CH2. And on this CH2 is equivalent to this, and on this CH3 is equivalent to this. I hope the points are clear. And there are three structural isomers therefore, but when a hydrogen atom from here is replaced by a chlorine atom, it becomes CHCl here, and this carbon becomes a chiral carbon. And therefore, for the second isomer, you will have both the dextro and levo forms. So for the first one, if the chlorine is substituted here, you have only one product. If the chlorine is substituted here, you have a product for which there are the dextro and levo isomers. Optical isomers are possible. That means you have two isomers. And so, in the third case, when a hydrogen is replaced by a chlorine here, of course, this carbon cannot be chiral. Why? Because on either sides you have ethyl groups. So it is not chiral. So there again you get only one isomer. So altogether, including the stereoisomers, you will have only 4 products in the case of the first compound. I hope you understand the point. It is CH3, monochlorination, one product, CH2 at the second carbon atom, monochlorination, but it becomes a chiral carbon then, and therefore you have two isomeric compounds, the dextro and the levo isomers. When you replace a hydrogen atom at the third carbon, you are getting a compound which doesn't show optical activity because the carbon is not chiral. So there is only one structure, right? So altogether you have 4 isomeric structures of the monochloro compound starting from the compound A, that is normal pentane. And if you take the second compound is this, that is neopentane. This is C, you have CH3, 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 and this also is CH3. And all the 4 CH3 are equivalent, isn't it? All the 4 CH3 are equivalent. So whichever CH3 you chlorinate, monochlorinate, you get one and the same product. So that means this compound on monochlorination gives a single monochloro derivative. The CH3 becomes CH2Cl. Either this or this or this or this. Whichever is substituted, you get one and the same compound, what is generally called as a neopentyl chloride. So neopentane on monochlorination gives neopentyl chloride, and that is the only compound possible. So you have only one isomer, one isomeric compound. Only one compound, one monochloro compound, no other isomeric compound possible from structure B. So obviously structure D will be the correct, but you have to see whether structure D is correct. Take the structure D. This is the structure D. That means CH3, CH, CH3, CH2, CH3. What you call isopentane. This is normal pentane, this is neopentane, and this is isopentane. And why isopentane? Because you have a methyl group on the second carbon atom. The prefix iso is added along with the name when the structure has a methyl group at the second carbon atom. Okay, so this is isobutane. That is the conventional name, and is actually 2-methyl butane, 2-methyl isopentane or 2-methyl butane. This is 2-methyl butane. Okay, now let us see how many monochloro derivatives are possible for this compound. How many monochloro derivatives? If a hydrogen at this carbon is substituted at the carbon number, this is carbon number 1, this is carbon number 1, at this carbon it is substituted, or at this carbon is substituted, these two are equivalent, then you have CH2Cl group here. And CH2Cl group here means CH2Cl, CH3, H, then CH to CH. That means this carbon atom becomes chiral. That means on substituting a hydrogen atom by chlorine on the first carbon, you have a compound which is chiral and therefore can give rise to two isomers, the dextro and levo isomers. So what I mean to say is, on substitution of a hydrogen atom by chlorine, monochlorination at carbon number 1, you are getting two isomeric compounds. Okay? Now when you do the chlorination at this carbon, the second carbon, at this carbon, what happens? You have the product CH3, okay, CCH3, Cl, CH2Cl, and that is only one compound. So substitution of a hydrogen atom at the second carbon gives only one compound, Substitution of the first carbon atom gives a pair of compounds which are optical isomers. Two compounds are there, and substitution of a hydrogen atom by chlorine at the second carbon gives only one compound. This carbon is not chiral. Now if you substitute this carbon, that is a third carbon, a hydrogen atom of the third carbon by a chlorine, what's the product that you get? CH3, CCH3, okay, then CH, and here you have CH, Cl, CH3. That means this carbon becomes a chiral carbon. And again, a chiral carbon means you get a dextro compound and a levo compound. That means you get two isomers. And on substitution of a hydrogen atom at this carbon, the last carbon, the fourth carbon there in the chain, this becomes CH2Cl and you get one isomer there. So how many monochloro products are possible? You are having 6 monochloro products, where you count not only the structural isomers but also the stereoisomers. When you are asked a question like this, all the isomeric compounds have to be taken into consideration. You take into account not only the structural isomers but also the stereoisomers, and altogether you have 6 isomeric compounds. The possibilities, you have 6 possibilities, altogether 6 possibilities for the compound 3, that is 2-methyl butane or isopentane. So I repeat, now the thing can be asked in various ways. This is one question. Similarly, you may be asked a question like this: how many monochloro derivatives are possible for isopentane? There are 4 structural isomers and 2 of which are chiral, and therefore altogether you have 6 isomers including the stereoisomers. For neopentane, you have just one isomer, that is neopentyl chloride, whereas from normal pentane, as we have said, you have 3 structural isomers, of which one exhibits isomerism, optical isomerism, and therefore altogether you have 3 plus 1, 4 isomers. Total number of isomeric compounds possible is 4. Now when questions of this type are asked, unless it is specifically mentioned, remember you will have to take into account all the possible isomeric compounds, both structural isomers and stereoisomers. But suppose the question is about structural isomers only, then you need count only the structural isomers. So while answering such questions, please take care the wording of the question. If I have simply said how many or 6 monochloro compounds, it means there are 6 monochloro derivatives, altogether 6 monochloro derivatives, by counting the structural isomers as well as the stereoisomers. Do you follow? So that's coming to the next question. Okay, next question. Yes, the order of stability of the carbocation. This is a very standard question, a textbook literature discussed in all classrooms, and I think you know the answer. I need not explain too much on this. Actually, the 3 given, the first one is the allyl carbocation, the second is a normal propyl carbocation, and the third is the benzyl carbocation. And it is a textbook knowledge that the allyl and benzyl carbocations are exceptionally stable due to resonance. Of course, it appears that they are all primary carbocations, CH2 plus, here also CH2 plus. But this compound or this ion, CH2 double bond CH2, CH2 plus, okay, can have resonance stabilization like this, CH2, CH double bond CH2. So you have two equivalent resonating structures, and that makes the resonance so important that the molecule is stabilized to a large extent. So the allyl carbocation is highly stabilized by resonance. And similarly, this, that is a benzyl carbocation, that also stabilized by resonance. You know, that also stabilized by resonance. You can write various structures, double bond CH2, you have the positive charge now here, and suppose the electron, then you have the third structure, double bond CH2, positive charge comes here, and now shift up pi electrons like this, that is pi electron delocalization, what you call resonance, double bond CH2, and then the shift like this, and you have the fifth structure with the CH2 plus, okay, double bond, double bond, double bond. So the benzyl carbocation is actually a resonance hybrid of these 5 canonical structures, or these 5 limiting structures, or these 5 resonance structures. And you have studied relating to the concept of resonance that the larger the number of resonating structures, the greater the stability of the compound. In the first case, it is equivalent resonating structures and the stability is very high. And in this case, you have a large number of resonance structures, and that also makes resonance very important, and the molecule is stabilized to a large extent. So the point is that the allyl and the benzyl are much more stable than what is expected of them, because what you find them are primary carbocations. But in spite of the fact that they are primary carbocations, because of this resonance stabilization, they are highly stable. So there is a normal dictum regarding the stability of carbocations, tertiary greater than secondary greater than primary. Okay, that's there. But however, the stability may be decided by certain other factors. For example, in this case, it is resonance. The allyl carbocation is highly stabilized by resonance. The benzyl carbocation is also stabilized by resonance. So they are much more stable than the carbocation number 2. And if the stability is compared of the 2 allyl and benzyl, the benzyl seems to be slightly more stable than allyl. So it is 3, okay, greater than 1. Of course, there is only a small difference between the stabilities of these two. 3 is more stable than 1 by a small extent, which is much stabler than 2. So that is the order of stability. Benzyl greater than allyl, greater than propyl. That is the order of stability. I think it is something that you have studied in your class, because during the discussion about carbocations, this example is normally cited. So I hope all of you will be thorough with it. If you have forgotten the matter, now actually revive your memory that this is the order of stability, and the extremely high stability of the benzyl carbocation and then the allyl carbocation are due to the resonance stabilization of these carbocations. Okay, coming to question number 6. Question number 6, there is a description given in the question itself. There are some chemical reactions which produce only one product in large amount and others in minor amount. One product in large amount and the other products in small amounts. And these reactions are usually described as stereoselective reactions. Stereoselective reactions. One product is formed in larger amount, okay, quite larger amount. And if only one product is obtained, if only one product, if that product is the only product, say to the extent of something like 98% or more, then such reactions are known as stereospecific reactions. I hope the point is clear. If in a reaction, one product is formed as the major product to the extent of something like 75% or 80% or even 85%, and other compounds formed in minor percentages, then the reaction is described as a stereoselective reaction, okay? And if that product in the reaction is the only product in the reaction amounting to 98% or even more than 98%, then the reaction is called as stereospecific reaction. So that literature is already given there, okay? And now is given a reaction here. And what is this reaction? What is the substrate? The substrate is an alkene. In which alkene? It is butene. This compound is butene. It is butene. Okay? And what is the reaction? The reaction is a pretty simple reaction. It is catalytic hydrogenation, where instead of hydrogen you have taken heavy hydrogen or deuterium, D atoms instead of H atoms. But the reaction is exactly similar to the addition of hydrogen. The two hydrogen atoms are added to the double bond. And being catalytic reduction, remember the stereochemistry is cis addition. Catalytic addition is cis. Catalytic addition of hydrogen is always cis. So this compound given here is butene, which has a property of geometrical isomerism. And since the two methyl groups are on the same side of the molecule and the two hydrogen atoms are on the same side of the molecule, what is given in this question is cis butene. So to cis butene, when a cis addition of D2 happens, when a D2 molecule is added in a cis fashion, it is cis addition. Remember that catalytic addition is always cis. It is cis addition to a cis geometry. Okay, when it is cis addition, what will be the stereochemistry of the product obtained? The stereochemistry of the product will be miso product. It will have a miso product. And if it is again to a trans alkene, if it is a trans addition, you might have studied trans addition, then also the product is miso product. And suppose it is cis compound and then a trans addition, then the product is racemic product. And if it is a trans alkene to which you have cis addition, then also the product is racemic. So this is something that you can have in your mind always. To a cis alkene, a cis addition will give miso product. To a cis alkene, trans addition will give a racemic product. To a cis alkene, to a trans alkene, a cis addition will give a racemic product. Okay? To a trans alkene, if it is a trans addition, you will get a miso product. So these four ideas can be kept in mind, and questions of this sort can be very easily solved. Of course, the structures are given in the next slide. You can look at the next slide, and next slide is this compound A. A is the miso structure, isn't it? The miso structure, what do you mean by the miso structure? The miso structure has this sort of a plane of symmetry. The stereoisomer designated miso has a plane of symmetry and therefore is not optically active. So this is the miso structure and this is the compound obtained, and it's very clear even with this Fisher projection formula, it is very clear that the two D atoms are on the same side and the two H atoms are on the same side. That means the hydrogen atoms are on the same side and the deuterium atoms are on the same side. The hydrogen atoms are cis with respect to the original double bond, and the deuterium atoms, the two deuterium atoms are also cis. That means it is a cis-cis configuration with respect to hydrogen and with respect to deuterium, and that is the Miso compound. I think these are things which are usually discussed in class in detail, and I think all of you might have studied this, and you are sure to answer this question quite correct. Okay? Coming to question number 7, and here I think you will have to take into consideration a little bit of, one has to be a little bit careful answering this question. Actually, you have to identify 3 products, A, B, and C. In that sense, the question may seem to be a little bit tough, though there is not much of a toughness as far as the problem is concerned, the question is concerned, but still, for an average student, perhaps the question may appear to be slightly tough. So be very careful while answering the question. You have to identify the 3 products A, B, and C. A is the product in one reaction, and B and C are the products in the second reaction. And here it is a reaction. Both the reactions are peroxide initiated reactions. And you have studied the peroxide effect. And peroxides initiate the formation of free radicals. So addition in the presence of peroxides are free radical additions. The peroxide will generate the free radical from the adding molecule to the unsaturated molecule. In the first case, it is butadiene, 1,3-butadiene. 1,3-butadiene is CH2 double bond CH, CH double bond CH2, that is 1,3-butadiene, and the peroxide will generate the radicals Br dot and CCl3 dot. These are the radicals generated. So the radicals are to be added to the double bonds. But however, one has to be very clear about this butadiene. Butadiene is what you call a conjugated diene. What do you mean by conjugated? Conjugated means you have double bond, then a single bond, then a double bond. Then it is called a conjugated diene. And by virtue of resonance in conjugated dienes, there is a possibility that the structure CH double bond CH, CH2 minus. This sort of a structure is possible, and in fact this sort of a structure is more possible during an addition reaction, and therefore the addition reaction will take place at this position and at this position, that is the 1,4 positions rather than the 1,2 position, and therefore the product obtained would be a 1,4 addition product. So to a normal alkene it is a 1,2 addition product, but in the case of a conjugated diene it is most probably a 1,4 addition product. Remember that butadiene gives a 1,4 product in more amounts than a 1,2 product. So the major product in reaction number 1 is the one in which the free radicals Br dot and CCl3 have been added to the first carbon and the fourth carbon. Okay, the product would be CH2Br, CH double bond CH, CH2 CCl3. So that is the compound A. That is a compound A. So you can have the correct answer only if the structure A has this particular structure. This is the structure of A, CH2Br, CH double bond CH, CH2 CCl3. So look into the answers and see whether this structure is given as structure A. Structure A is given as this structure, CH2Br, CH double bond CH, CH-CCl3 in A, and in B it is again Br, CH double bond CH, CCl3. In B also it is given, and in C also it is given, and D also it is given actually. So the structure A is correctly given in all the 4 options. So obviously the correct answer will be decided by identifying the correct answers for the second addition reaction. So what is the second addition reaction? The second addition reaction is RCH double bond CH2 giving CCl4, and again that CCl4 in the presence of peroxide will dissociate to give the chlorine radical and the CCl3 dot radical. So it is Cl dot plus CCl3 dot, similar to Br dot plus CCl3 dot. Radicals are formed. Remember, it is due to the peroxide. Peroxides always help the generation of radicals. Peroxide, if it is present in a reaction, remember the reaction will follow a free radical mechanism. So in this case it is free radical substitution or free radical addition. In this case double bond means free radical addition reaction. So in the second compound it is RCH double bond CH2 is RCH double bond CH2. It can lead to 2 radicals. One is RCH dot CH2, that is one radical, and the other is RCH2 dot, suppose it is here, actually you can have this radical RCH2 CH dot CH2 radical, and this case it is RCH2 dot this radical here it may be a dot. Okay, so it is RCH dot CH2, it's not CH2 actually, the Cl dot has to come here, so it will be CH2 Cl CH dot, or it may be RCH Cl CH2 dot. When the Cl dot approaches the double bond, you can have these 2 possibilities, and in this possibility of these 2 possibilities, the radical which is secondary, as you know, will be more stable than primary. So obviously this radical will be formed in a greater proportion than this one, but these 2 possibilities do exist, and when the other radical CCl3 dot combines with this, you have the product RCH CCl3 CH2Cl. Okay, RCH CCl3 CH2Cl will be the product from this, and from this you will have the product RCHCl CH2 CCl3. But which is a major product? You have to decide. The major product is the one which is formed from the secondary radical, which is more stable than the primary radical. Do you follow? But suppose these 2 compounds are given as the options B and C, then things would have been fine. It would have been complete with answering that these 2 compounds from the free radical by combination with the CCl3 are the 2 products B and C. But C is given as a product quite different from this. So what is C given? The C given is a product having a structure like RCH CH2 CCl3 CH2 CHClR. So what is the possibility of forming a larger molecule than any of these? That can be explained by combination of these 2 radicals. Actually these 2 radicals, the first radical and the second radical during the formation of the compound. So that generates the product. The product RCH, okay, you have CH2 CCl3 RCHCl CH2, okay, CH2 CCl3 CH2 CCl3, and here's a dot combining with RCHCl CH2. So there is a radical recombination sort of reaction leading to the product given as C, leading to the product given as C in the options, C in the options, RCH, CH2CCl3, okay, CH2CH2R. Here also that option is given, RCH, CH2CCl3, CH2CHClR, and here also the option RCH, CH2CCl3, CH2CH2R, and here RCH, CH2CCl3, CH2CHClR. So here the option RCH, CH2CCl3, okay, RCH, CH2CCl3, CH2, okay, CHClR. So the first option was okay with all the 4 options. The first compound A was okay. Now the second compound RCHCl, CH2CCl3 is okay in the option B. Now the third compound formed by the recombination of these radicals is also in the option B, and therefore the option B seems to be the correct option, where the structures of A, B and C are correctly given. So slightly a bit difficult for you unless you think about this radical recombination reaction from the 2 radicals generated by RCH double bond CH2 on reaction with the Cl dot and on reaction with the CCl3 dot. You may not be actually able to find out what the compound C is. So I hope you have followed it. It is by the recombination of these 2 radicals, RCH-CH2-CCl3 and RCHCl-CH2, that you get the product RCH-CH2-CCl3-CH2-CHClR. That product in option B. That is correct. That is the compound C, and the compound A was already discussed, and this is the compound B, that is RCHCl, okay, CH2 CCl3, that is a compound which is formed as the major product in the second reaction, and C may be a minor product only, but that C is formed by recombination reactions between the 2 radicals. The 2 radicals combined forming this molecule. It is not the other minor product that we have already said about. This is again a minor product, radical recombination reaction that is possible. So the product is formed in minor proportions only, and that is given as the choice, and therefore you have to identify that. That's important. So that is that question, a slightly difficult question for you. I do admit, slightly difficult question. So only if you think about the various possibilities, you will be able to come to the answer. So slightly difficult for you. Okay. Now coming to the next question, that is question number 8. Which of the following reagents will lead to the correct conversion, given below? It's a very simple reaction, the conversion of benzene to this compound. What is that? You have this side chain. The side chain is CH2, C, CH3, CH3, CH3. Okay? So it's the neopentyl. Neopentyl structure has to be substituted at the benzene ring. And once you see that, every one of you may be recalling the Friedel and Krauss alkylation. That is the immediate thing that may be coming to your mind. But what are the options given here? The first option is a Friedel-Krauss reaction with the neopentyl alcohol, CH3CCH3, CH3CH2OH, in the presence of a Lewis acid BF3. Of course, Friedel and Krauss reaction, whether it is alkylation or acylation, it involves a Lewis acid catalyst. Normally it is anhydrous aluminum chloride, but BF3 also would serve as a catalyst because BF3 is basically electron deficient. So BF3 can catalyze Friedel-Krauss reaction, no problem. But the point is, from this neopentyl alcohol, what will be the carbocation generated? The carbocation generated will be this one. The carbocation generated will be this one. That is the neopentyl carbocation. And the neopentyl carbocation being a primary carbocation. Remember the possibility of rearrangement. This methyl group may migrate to this position and you have CH3, CH3, CH2, CH3, which is a tertiary carbocation, more stable than primary carbocation. So this is the carbocation that you get in option A. And therefore, you won't get the desired product. The desired product must contain this neopentyl unit. But here the unit is not neopentyl, it is isopentyl unit. This is isopentyl carbocation. And the third also it is there. In the third case, CH3 thrice CCH2X in the presence of AlCl3, that also will generate CH3 thrice CCH2 positive. Exactly this carbocation which will rearrange again forming this one, the isopentyl carbocation. So you will get only isopentyl benzene in reactions A and B. So those two options cannot be given. Okay? Then what else is the method? The third option given is a different reaction which is with an acid chloride in the presence of AlCl3. That's the Friedel-Crafts acylation. Okay? So Friedel-Crafts acylation of benzene with this compound will give you CO, then C, CH3, CH3, CH3. Okay? So those three CH3 are always there. So this part is okay, but here it is a CO group. In acylation, what you get is a ketone. So you are not getting a hydrocarbon. You get a hydrocarbon only in alkylation. Do you follow? So you have to do another reaction by which the carbonyl group has to be converted into a CH2 group. And there are two well-known reactions in your mind, I suppose. One is the Clemenson's reduction by treating with a zinc amalgam and concentrated HCl, that will convert the CO group into CH2. And the second is the Wolff-Kirchner reduction, which will also convert the carbonyl group into a methylene group. And here the option given is the Wolff-Kirchner reduction. And the Wolff-Kirchner reduction is the reduction with the hydrogen, NH2, and a base. When you see that NH2 and base, you must remember that it is Wolff-Kirchner reduction. This is the reaction, Wolff-Kirchner reduction, okay, in which the CO group is converted into CH2 group. An equally efficient method is Clemenson's reduction, but what is given here is the Wolff-Kirchner reduction. So that will convert the CO into CH2, and once this is CH2, you have the desired product. So the option is C. C is the correct option for the above conversion. I think it is clear. It is again about carbocations. And remember the chemistry of carbocations. Wherever you have question about carbocations, you will get plenty of questions, in fact, in various question papers about reactions involving carbocations. And remember that in all such reactions, there are rearrangements possible. So here at first sight, you may think a carbocation CH2 plus, and here also CH2 plus. But remember that carbocation, the neopentyl carbocation, will rearrange to form the isopentyl carbocation by a methyl shift. Normally it is a hydrogen shift or a methyl shift that takes place to the adjacent carbon, carrying the positive charge. If that is possible, then the rearrangement occurs, and the primary to secondary, which is more stable, or the primary to tertiary, which is more stable, or the secondary to tertiary, which is more stable. And that is a routine thing as far as reactions, the carbocations are concerned. So wherever you come across reactions involving carbocations, always use your mind to see whether there is a possibility for rearrangement. Okay? So there will be definitely questions on carbocation rearrangement in question papers. In almost all question papers, if you search the previous question papers, you will see that the question papers do contain questions relating to carbocation chemistry, and most of these questions asked will contain a rearrangement of carbocation. Remember that in your. Okay, so that's why A and B are not correct options here, because the carbocation will undergo rearrangement to give isopentyl carbocation, and therefore the product obtained will be isopentyl benzene and not neopentyl benzene. So neopentyl benzene can be obtained only by the third method, a two-step conversion by reaction with an acid chloride to give a ketone, and this ketone is subjected to the Wolff-Kishner reduction or the Clemenson's reduction. And here what is given is Wolff-Kishner reduction. It is hydrazine and base. If it is Clemenson's reduction, it is zinc amalgam and concentrated HCl. Okay, I hope it is clear. I'm coming to question number 9. It's a pretty simple question. Very, very simple. I already told you during my previous class, for the JEE main question paper, you will have 25 questions, at least some 7 to 8 questions, sorry, will be very simple questions, which an average student will find very easy to answer. And another some 8-7 questions will be slightly above average questions. Only with a little bit of thinking, you will be able to answer those questions. And then will be another 6 or 7 questions, which may be questions of a really relatively higher standard, which requires a little more thinking. So that is usually the composition of the JEE main question paper. And this particular question belongs to the first category I told you, very easy questions. So what is it? CH3, CH2, CH3, isn't it? It is again photochemical chlorination. So photochemical chlorination, you can form a free radical either here or a free radical here. Okay? Photochemical chlorinations are always free radical substitutions. I already told you in the previous question, in connection with one of the previous questions. So you have CH3, CH2, CH2 dot, as well as CH3, CH dot, CH3. These are the two possible free radicals from this molecule on reaction with chlorine radical, right? Okay. So what is the major one? The major one will correspond to the most stable free radical. And the more stable free radical is the secondary free radical. And this is the secondary free radical, the isopropyl free radical. So the product is CH3, CH, Cl, CH3. So that is the major product. And this compound is then treated with the magnesium and reaction of an alkyl halide with the magnesium. Again, the reaction is very simple. It is a Grignard reagent that is formed. So what is the Grignard reagent formed from here? On reaction with the magnesium, you have CH3, CH, MgCl, CH3. The isopropyl magnesium chloride is a Grignard reagent. Very simple. And the next step is the reaction with the D2O. D2O. The reaction with the D2O is similar to the reaction with H2O. If it were H2O, what would have been the reaction? The reaction would be the carbanion part of the Grignard reagent, that is this part, CH3CH, CH3 minus. The methyl is positive, and therefore there is a negative charge on the carbon, and that's why you call it carbanion. Grignard reagent has a carbanion structure. It is CH3, or if you write Rx and Mg, it is RMgx and RMgx R minus Mg plus. So the carbanion part of the Grignard reagent, okay, that will take a hydrogen from H2O to give a molecule of hydrocarbon. That's the reaction. RMgX with H2O, the reaction would be HOH. The product is RH. The R takes the H from H2O, okay, and the other product is MgXOH. Actually, there are similar reactions. While these things are taught in the class, very often the teacher may be telling you that the reaction with water, reaction with an alcohol molecule, reaction with a phenol molecule, reaction with a primary amine, or reaction with a secondary amine, or reaction with a terminal alkyne. In all these reactions of Grignard reagent with these compounds, it is the carbanion part of the Grignard reagent, that is R of the Grignard reagent, taking a hydrogen from the compound, forming a molecule of hydrocarbon. You get a molecule of the hydrocarbon as a product. So what is the reaction in this case? Instead of H2O, it is D2O. Then the Grignard reagent, the carbanion part of the Grignard reagent, that R minus, will take a deuterium atom, forming a deuterated hydrocarbon as a product. Right? So in this case, the hydrocarbon would be CH3. Okay? Here you have C, here CH3, and you have an H here, and this negative charge here, it takes, the carbanion takes a deuterium atom from D2O, and this is the product that you get. The product that you get is CH3, CHD, CH3, CHD, CH3. That is the product obtained in the reaction. Okay? CH3, okay? H, CH, that H is already there. And D, CH3 is the product. That is the correct choice. The correct choice is C. The correct choice is C. This is the correct choice of the question. The product formed is CH3, CH, D, CH3. Okay? So it is photochemical chlorination. Think of the stability of the free radicals. The secondary free radical is more stable. So the first part is solved. You get secondary free radical. Then chlorine dot combining with it, forming secondary halide, that is in this case isopropyl chloride. And this isopropyl chloride on reaction with the magnesium gives the Grignard reagent isopropyl magnesium halide, and the isopropyl magnesium halide contains that isopropyl with a negative charge, and that means it's a carbanion type structure for Grignard reagent. The magnesium is positive and the other part is negative. There is CH3, CH3 part is negative, and that carbanion part of the Grignard reagent on reaction with a molecule containing active hydrogen takes the hydrogen, forming a molecule of hydrocarbon. This is the thing that you have to keep in mind. In this case, instead of H2O, it is D2O, therefore it takes a D atom instead of hydrogen atom, and therefore the product obtained is CH3, CHD, CH3 as the product. Okay, that is correct option is C. C is the correct option in this case. I hope you are following what I say. Now coming to question 10. At least in one of the JEE main question paper, you will get a question on nomenclature. Not all papers may contain question on nomenclature. There are various sessions for the JEE main exam, as you know. At least for 1 or 2 or 3 sessions, you may get question on nomenclature. Usually, the compound is given, you are asked to write the name. But here, the opposite thing is there. You are given the name of the compound, and you are asked to identify the structure corresponding to the name. But however, if you look at the options, you will see that the options are pretty simple. All the options contain the bromine, chlorine and acid group in the same positions. And if it is a carboxyl acid, as you know, or the functional groups, the highest priority is for the COH group. So the COH group has to be numbered as carbon number 1. So this is carbon number 1. This is carbon 2. This is 3. This is 4. This is 5. This is 6. And this is 7. And that's the case with all the 4 structures. That means there is no dispute about the position of acid, position of chlorine, and position of bromine. Acid group is carbon number 1. 1, 2, 3, 4, 5. Chlorine is at 5. 5 chloro. And bromine is at 6. 6 bromo. That is also correct. And then you have a methyl group at the second carbon. That is also correct. This is a methyl group. That is also correct. So all these are there in all the 4 options. The positions of all the groups are okay. Except one. What is that? 5-ethoxy carbonyl. And ethoxy carbonyl is given as this in one compound, this in the second compound, and this in the third compound, and this in the fourth compound. So to answer the question, what you need to know is only the structure of ethoxy carbonyl. Which group is called ethoxy carbonyl? That is the only thing that you must know. Ethoxy carbonyl. Ethoxy is OC2H5. Okay? Carbonyl is CO. So ethoxy carbonyl is COOC2H5. Quite simple. So this group, which is an ester group, as far as IUPAC nomenclature is concerned, this has to be named as just one group, and then this group which appears as a substituent in the main structure can be named as ethoxy carbonyl. COC2H5 is ethoxy carbonyl group. So that's the only thing you must know to spell out the correct structure. So ethoxy carbonyl is COOC2H, is actually C double bond O C2H5, that is COOC2H5. And the other structures in A, C and D are not COOC2H5. So naturally the correct option is B. B is the correct option. It's a pretty simple question. I think all of you can answer this question, but only thing is that you must know what this ethoxy carbonyl group is. Ethoxy is OC2H5, carbonyl is CO, and ethoxy carbonyl is COOC2H5. Just one group, COOC2H5 group. It is actually an ester group. Okay? So this ester group is ethoxy carbonyl in IUPAC nomenclature. I find some difficulty in erasing. Okay, coming to question number 11. Sorry for the loss of a few seconds. I found some inconvenience in erasing what was written. That was the reason why it's a bit delayed. Sorry for that. Coming to question number 11. Which of the following on adding 1 molecule of hydrogen per molecule of the compound can result in a compound capable of exhibiting stereoisomerism? That again is a pretty simple question. I think all of you will be able to answer this question. That belongs to the category of the simple questions. I told you there will be some questions which are pretty simple, can be answered by all of you. And I do hope that all of you will be able to answer all the other questions too for the coming JEE examination. Okay? So here is the compound CH3CN. CH3 triple bond. This is the compound CH3CN. On the addition of one molecule of hydrogen, just one molecule of hydrogen to this compound, what will be the product formed? The product formed will be CH3 double bond N. You have a hydrogen atom, and here you have a hydrogen atom. Of course, remember that the nitrogen here has a lone pair. And this molecule, look at the molecule carefully. You will see that this molecule is something which can exhibit geometrical isomerism. The two hydrogen atoms may be on opposite sides, or the two hydrogen atoms may be on the same side of the C double bond N, which is planar. So about the plane of the molecule, the alignment of the two hydrogen atoms can be either cis, what is generally called as a syn compound, or the hydrogen atoms may be on opposite sides of the plane, then it is called the anti compound. So you have geometrical isomerism for this compound. Okay, you have geometrical isomerism for this compound. Stereoisomerism. It's a case of stereoisomerism. And now what about the second compound, CH3CONH2? CH3CONH2. Is to reduce this compound with H2, 1 mole of H2, 2 hydrogen atoms. At this bond, C double bond O, what is the product? CH3CH OH-NH2. And what you find is this carbon is now chiral. Chiral means it can exhibit optical isomerism. So the second compound exhibits optical isomerism. Now what about the third compound? Third compound is acetylene. Okay, acetylene. Okay, adds 1 molecule of H2. You have ethylene. In the ethylene, as you know, doesn't exhibit geometrical isomerism. It is not chiral and therefore doesn't exhibit optical isomerism. So the third molecule C, it doesn't exhibit stereoisomerism. Okay, and what about the last molecule? The last molecule, this molecule can add a molecule of H2, and you have this compound CH double bond CH phenyl group, and here with respect to the double bond, the two hydrogen atoms may be placed cis or trans with respect to each other, and this compound is also a compound which exhibits geometrical isomerism. Geometrical isomerism. It has cis and trans isomers. So of the 4 compounds, compound A can exhibit geometrical isomerism, compound B can exhibit optical isomerism, and compound D can exhibit geometrical isomerism. So the correct options are A, B and D. Actually, the options would have been given something like A, B, D, B, D, or A, B, C, D, all A, B, like that. 4 options would have been given, and the correct option would be A, B, D. Or this question may be appearing as a more than one answer type question in the IIT Advanced, where you have all the 3 options A, B and D correct. They exhibit stereoisomerism. A exhibits geometrical isomerism, B exhibits optical isomerism, and D exhibits again geometrical isomerism. It's a pretty simple question. I think all of you can answer that question without making any mistakes. Now here is a question which is again about the basic things like resonance, tautomerism, okay, and geometrical isomerism, diastereomerism, and so on. These are the terms that you listen to while you discuss stereochemistry of compounds. Okay? And once this question is asked, we will take a short break. So let us go to the answers. The question is about the correct statements concerning the structure E, F and G. Okay? Look at the structures very carefully. Look at the structures very carefully. Now in structure E is a carbonyl compound. Okay, it's a carbonyl compound. It has a hydrogen atom here. Don't forget that. It is not written there, but remember that there is a hydrogen atom here. So this hydrogen atom of that compound, CH3, CH2, okay, here you have CH3, and here you have a hydrogen atom, and then you have COCH3, that's a compound. So this hydrogen atom is present on a carbon which is adjacent to a carbonyl group, means this pi bond can shift to this double bond and the hydrogen can be shifted to the oxygen atom. So that's the case of tautomerism. So here it's a case of tautomerism. This compound can undergo tautomerism and can exist in the structure CH3, CH2, C, okay, double bond C, OH, CH3, CH3. That is the structure F. So the E structure, this is a structure E, it tautomerizes into the structure F. That means E and F are tautomers. They are never resonance structures. In resonance, remember, it is delocalization of pi electrons. But here it is, of course, there is a delocalization of the pi electrons, but along with that there is migration of hydrogen from the second carbon. Then only it's a case of tautomerism. It's a ketone here, and that is getting transformed into the enolic structure. This is the enol. So structure F given in the question is a tautomer of structure E. Now what is the structure G? Look at the structure G carefully. Look at F and then look at G. What is the difference? In the structure F, the ethyl group and OH are on the same side. In the structure G, the ethyl group and of course this is the ethyl group and the OH group are on opposite sides. In the structure F, the two methyl groups are on the same side, whereas in the structure G, the two methyl groups are on opposite side. And what is the situation? F and G are geometrical isomers. F and G are geometrical isomers. Geometrical isomers. F and G are related as geometrical isomers. E and F are related as tautomers. And obviously, E and G also will be related as tautomers. E and G also will be related as tautomers, because E tautomerizes to give F and G is a geometrical isomer of F, means E can tautomerize to give G also. So E and F are tautomers, E and G are tautomers, F and G are geometrical isomers. So statement B is correct, okay, and statement C is also correct. I hope you follow the point. Structure E and structure F are related as tautomers. Structure E and structure G are related as tautomers. F and G are related as geometrical isomers. Therefore, the statement B and C are correct. But the statement 1 is not correct, because it is given that E, F, G are resonance structures, which is not true. They are not resonance structures. They are tautomeric structures. They are geometrical isomers. F and G are geometrical isomers. E, F are tautomers. E and G are tautomers. And now is the last statement. F and G are diastereomers. So there some students may have some confusion. Now what are diastereomers? What are diastereomers? What is the definition of diastereomers? Listen to me carefully. Diastereomers are stereoisomers which are not mirror images of each other. That's a definition. Stereoisomers which are mirror images of each other are known as enantiomers, and stereoisomers which are not mirror images of each other are known as diastereomers. So geometrical isomers are stereoisomers, but they are not mirror images of each other. And therefore, geometrical isomers can also be included in the category of diastereomers. Do you follow that? That's a very general definition of diastereomers. Diastereomers are compounds. They are stereoisomers. I repeat, diastereomers are stereoisomers which are not mirror images of each other. And therefore, in the present case, the geometrical isomers which are not mirror images of each other can also be included in the category of diastereomers, and therefore F and G are diastereomers. That statement is also correct. So you have again a more than one answer type question. You have B, C, D. The three answers are correct for this question. Okay, this may be asked as a multiple choice question provided you are given choices like all A, B, C, D, A, B, C, B, C. So that's the type of question that may be asked if it's a multiple choice question. If it is a more than one answer type question in advanced, then the question may be like this, where you have three options which are correct, and in this case you find B, C, D are correct. Rather than deciding which options are correct, our purpose of discussion is to understand the chemistry involved in the question. That's very important. For each question, there is a lot of chemistry involved. Remember that these questions are something special. Some special questions, some questions, really good questions where you have to think a lot and you have to understand more than one principle to answer the question. So here must know what is meant by diastereomerism, what is meant by optical isomerism, what is meant by geometrical isomerism, and what is the relationship between geometrical isomers, what is tautomerism, and what is the relationship between the tautomers. All these things you must know, then only you will be able to answer such a question correctly. But the question is not difficult, I tell you. Only thing is that you must know these basic principles with clarity. So question E and F, structures E and F are tautomers, structures E and G are tautomers, structures F and G are geometrical isomers. And geometrical isomers can also be, I repeat, can also be included in diastereomers, because the definition of diastereomers is this: they are stereoisomers which are not mirror images of each other. Therefore, the geometrical isomers can also be considered as diastereomers. Okay, so let us take a short break of 2 minutes or 3 minutes. Okay, you will bear with me, I suppose. Welcome back. Let us continue. Slide. Yes, that is question number 13. Again, a question relating to stereochemistry. I have purposefully included more questions from stereochemistry because that's a point where students often many of them have not the correct knowledge or correct information or correct knowledge about these things, because you have to give thrust, you have to focus on questions of this type with the stereochemistry. That's very important. So here is a question which was asked in one of the previous question papers. Now this question is regarding the absolute configuration of this compound. And I hope you can identify what this compound is. It is a compound. If I write in the Fischer's projection, we see OH, H, C, H, OH. Okay, that's the compound. So this compound, I hope all of you know, is tartaric acid. So that's the compound, tartaric acid, 2,3-dihydroxybutane, 1,4-dioic acid. That's IUPAC name of the compound, and that is tartaric acid. And corresponding to what has been drawn in the question, if you write down the Fischer's projection formula, it will be like this: COOH, COHH, CHOH, COOH. Okay? So that is tartaric acid. So what will be the absolute configuration given in terms of R and S? How will you assign the R and S symbols for the absolute configuration of the groups about these carbon atoms? These are the carbon atoms to be considered. So one way of understanding this is to write down the groups about this carbon in such a way that you write the hydrogen top here, which is possible if you rotate this part of the molecule, and then the OH group will be here and the other group will be here. And in that case, remembering the priorities of groups, in the molecule, the priority is for OH, because the atomic number of oxygen which is linked to carbon is 8, whereas atomic number of hydrogen is 1, that is kept atop, and the atomic number of carbon is 6. The priorities are decided on the basis of the atomic numbers of the atom linking to the carbon atom. So the priority is 8 for OH and 6 for COOH. And of course, there will be a priority for this group as a whole with respect to the first carbon. And if you take the direction of the priority from the highest priority to the lowest priority, you will see that it is this direction. So this direction means an anti-clockwise direction. An anti-clockwise direction means the absolute configuration is yes. So with respect to the carbon, this carbon, which is carbon number 2, with respect to carbon number 2, the absolute configuration of the groups is yes. And in a similar way, you can also show that the absolute configuration about this unit, or with respect to the third carbon atom, is also S. And therefore, the absolute configuration is put as yes. Okay? So remember that this is optically active. So you have the mirror image, and that will have the configuration RR. Okay? And for the tartaric acid, if this is the molecule COH, COHH, COHH, COH, then this is Misotataric acid, because it has a plane of symmetry. It divides the molecule into two equal halves, which are mirror images of each other. And therefore, this is a plane of symmetry, and for the molecule is optically inactive, and this isomer of tartaric acid is called Misotataric acid. And for Misotataric acid, if one is R, the other will be S. Therefore, the configuration will be RS or SR, which are equivalent in the case of Misotataric acid. So actually, you have only 3 tartaric acid. One is having the configuration RR, the other is having the configuration SS. These are mirror images of each other. And then you have the third one, which is RS or SR. Both are equivalent in this case. In this case, because these are similar chiral carbon atoms. On both the carbon atoms, you have HOH and COH. So similar chiral carbon atoms. And in that case, you have only 3. You have only 3 stereoisomers, a pair of enantiomers, and a mesoform. And the pair of enantiomers have the configurations RR and SS, and the mesoform has the configuration RS or ESR. Both are equal in this case. And for the compound given, the configuration works out to be SS, as I already explained. So it is important that you must know such simple examples where the absolute configuration can be given. And this is a question which was asked previously. And when question of this type is given, try to give the Fisher projection formula, and then look at the groups, decide the priority, and the priority, the highest priority to the lowest priority, the direction of which is noted. If it is clockwise, it is R, and if it is anti-clockwise, it is S. And you may be knowing that the R comes from the word rectus. Rectus means towards right, and S comes from the word sinister, which means left. So if the direction is to the left, it is sinister or S. If the direction is towards the right, that is clockwise, it is designated as R. And this is the method of giving absolute configurations to stereoisomers. And one example is that of tartaric acid, which you might have studied while we discussed this aspect. But this aspect used to be taught either in the first year or in the second year when we discuss haloalkanes and haloarenes. But now that you have completed both years, there is no problem in asking this type of a question along with basic organic chemistry and chemistry of hydrocarbons. That's why this question is put here. And I think the details are quite clear to you. And you can answer similar questions with this sort of a knowledge, having this sort of a knowledge. Okay. Now comes another question, again about isomerism. Consider all possible isomeric ketones and their stereoisomers of molecular weight 100. Molecular weight 100. So you'll have to try. What will be the formula of the ketone? Molecular weight 100 means you have how many carbon atoms? What is actually the formula of a ketone? You can actually start from acetone. So what is the formula of a ketone? That's the simplest ketone that you can think of. It is C2, C3, H6O. So it means the formula of a ketone, if it has 3 carbon atoms, 6 hydrogen atoms and 1 oxygen. And extending this principle, the relative proportions of carbon, hydrogen and oxygen in ketones, if it has a molecular mass 100, it means it is a hexanone. Hexanone means, if you write the symbol hexanone, CH3CH2, CH2, CH2, COCH3. It has 6 carbon atoms, so the atomic mass 6 into 12, that is 72. Then it has 12 hydrogen atoms, 12, and it has 1 oxygen atom, 16, making a total of 100. Okay, so knowing the formula has a 1:2 for carbon and hydrogen, C3H6 and 1 oxygen, you can calculate the molecular mass for the next compound or the next compound or the next compound. You take the 5 carbon compound and see the molecular mass is not 100, and then take the 6 carbon compound, you find that the molecular mass is okay, that is 100. So that is the first thing that you must do in answering this question. So it's a hexanone. So how many isomers are there for hexanone? That's the next question. How many isomers? So this is the one. Okay. Then what is 2? Number 2. The hexanone can have a carbonyl group here. Carbonyl group here at the second carbon. At the third carbon. Okay. At this carbon, you have the carbonyl group. CH2, CH3. So this is what you call 2-hexanone, and this is what you call 3-hexanone. And if it is carbonyl group here, then also you have the same compound. So in the straight chain, you have only 2 possibilities. One is 2-hexanone, and the other is 2-hexanone, and the other is 3-hexanone. Okay? And then take the branched compounds possible. What are the branched compounds possible? You take 5 carbon atom chain and put a methyl group somewhere here. You cannot have a methyl group on the carbonyl carbon because here all the valencies are satisfied. So you can have a methyl group here, then the compound is CH3, CH2, CH, no hydrogen here, this is CH, that's the compound. You have a methyl group on the third carbon atom from this side. You can also have a methyl group on this carbon. So you can have the fourth compound, CH3, CH, CH3, okay? CH2, then you have CO, CH3. So that is the fourth compound. So here the carbonyl group is carbon number 2. Here the carbonyl group is carbon number 2. But the methyl group is on carbon number 3. And here the methyl group is on carbon number 4. So there are the 2 isomers. Okay. Then structure number 5. You must practice like this. Structure number 5 is the one containing 4 carbon atoms. And you put a carbonyl group here. And then you have 2 more carbon atoms. So how will you place the 2 more carbon atoms? You can put the carbon atom here as methyl group, and here also methyl group. So this is the next compound. Okay. This is the next compound. Right? Is there any other ketone? That's the question. Is there any other ketone? Can you have any other ketone? You have 1, 2, 3, 4, 5. You have any other ketone. Any other ketone is possible. You will have a ketone like this. A ketone with a structure CH3 you have CH3, okay, CH2, CH3 is CH3, okay. We already written that. CH2 COCH3, CH3 CH2 CH3 COCH3 also we have written. Then why can't you have a structure CH3 CH2 CH3 CH2, okay, CO, okay, CH3. That is also possible. So you find six structures are possible. One is 2-hexanone, this is 3-hexanone, this is 3-methyl-2-pentanone, and this is 4-methyl-2-pentanone, and this is 2-methyl-3-pentanone, and this is 3,3-dimethyl-butanone. 6 structures are possible. 6 structural isomers are possible for a ketone of molecular weight 100. Of course, you will have to try, then only you can get it. Okay? Now look at these structures carefully. If you reduce these structures, the CO group will be converted into CHOH group. That means the group will become chiral, and therefore you will always get a mixture of plus minus forms during reduction by sodium borohydride. Right? And in this case also it is CHOH. Therefore this point will become chiral. In this case also it will be chiral. In all the cases, the reduction of the carbonyl group will induce a chiral center in the molecule, will give a chiral center in the molecule, and therefore you will get a mixture of the dextro and levo products during the reduction process with the sodium borohydride. But if you look at this molecule, that is structure number 3 here. Structure number 3, look at this carbon. This carbon has an ethyl group, has a methyl group, has a hydrogen atom, has a COCH3 group. That means this carbon atom is chiral. Among the 6 isomeric compounds, only this isomer has a chiral carbon atom. And if it already has a chiral carbon atom, it can exist in the dextro form, it can exist in the levo form. So truly speaking, there will be 6 plus 1, there will be 7 isomers. Total number of isomers will be 7. There will be 5 isomers plus an isomer which can exist in dextro form and levo form. So altogether you have total number of isomers for such a question will be 7. Okay? And this particular isomer, remember, on reduction by hydrogen, it is already the dextro isomer reduced at the CO group, and the CO group becomes CHOH and the carbon becomes chiral. That means the dextro compound itself gets reduced into 2 stereoisomers corresponding to the dextro and levo isomer generated at the reduction point. The CO becomes CHOH. I hope you understand the point. Similarly, the levo also can give rise to 2 products, which means the reduction of the 2 enantiomers of this compound, that is 3, can give products which represent a pair of pairs of diastereomers. Do you follow? The remaining 5 compounds, that is compound number 1, compound number 2, compound number 4, compound number 5, and compound number 6. These 6 compounds on reduction of the carbonyl group will give a mixture of the dextro and levo forms, because it's only after reduction the molecule becomes chiral. The molecule before reduction is not chiral. Before reduction is chiral only with respect to the compound 3. That's why in the case of the compound 3, you get 2 pairs of enantiomers after reduction. Whereas in the case of the remaining 5 compounds, which are not chiral before reduction, become chiral after reduction. And since a new chiral center is generated, you can have either the dextro compound or the levo compound as a product. That means you will get a mixture of the dextro and levo. That mixture, 1:1 mixture of the dextro and levo, is what you call as the racemic compound. So the 5 ketones will give racemic product during reduction, whereas the 1 ketone which was chiral before reduction, that is the compound 3, it was chiral before reduction. This compound will give 2 pairs of diastereomers during the reduction. You have the dextro, you have the levo. The dextro is reduced, the levo is reduced, and therefore you get products which constitute 2 pairs of diastereomers. I hope you understand the point. So that's a good question. First of all, corresponding to molecular weight 100, you have to decide which is a ketone. So that is something that you can do within seconds. Molecular weight must be 100, and therefore it's a hexanone. Then writing the isomeric forms, try the isomeric forms. But since for examination you are not getting enough time to write all the structures, it is enough you write the carbon skeleton, the skeleton structures, and try what are the possibilities. It may be hexane 3-on, it may be hexane 2-on, 2 cases. And then for pendant structures, you have 1, 2, 3, 3-methyl 2-pentanone, and then you have 1, 2, 3, 4, 4-methyl 2-pentanone, and then you have 1, 2, 3, 2-methyl 3-pentanone. They are the pentanone structures. And then you have only 1 butanone structure, that is 3,3-dimethyl butanone. And look at the structures. In C, the carbonyl group is reduced to CHOH, and there will be generating a chiral center in the molecule. So in all reduction process except for the compound 3, you get racemic mixtures. And for the compound 3, since there are already dextro and levo isomers, both will get reduced, generating 1 more chiral center in the molecule, and therefore you will get 2 pairs of diastereomers as a product. I hope you understand the point. So that's a good question. You have to spend some time on this. Otherwise, you are likely to commit mistakes. Okay? So we have to rush, otherwise we won't be able to complete. Coming to question number 15. A hydrocarbon with molecular formula C6H8 is chiral. Now this is the question belonging to the first category because the very simple questions. Okay? The C6H8. But upon catalytic hydrogenation, it gives an chiral carbon. Okay? C6H8 is chiral. That is what is given. But upon catalytic hydrogenation, it gives an chiral hydrocarbon of molecular mass 86. So C6H8 is becoming C6, how much? 86. For the molecular mass, 86. For 6 carbons, 6 into 12 is 72. So the remaining is hydrogen. You have 14 hydrogen, then only it is 86. That means the molecular formula is C6H14. And it's very simple to note that this formula corresponds to CnH2n plus 2. That means this is an alkane. This compound is an alkane. And this compound has 6 hydrogen atoms short of this molecule. 6 hydrogen atoms short means the compound may contain 3 double bonds. Okay? It may contain 3 double bonds, or it can contain a ring and 2 double bonds. Okay? There are the various possibilities. But the reduction product is an alkane, that is a straight chain compound. If the reduction product is a straight chain compound, I think you need not worry too much about the question, because that excludes the possibility of a cyclic compound as a substrate. A cyclic compound or reduction will give only cycloalkane as a final product. If it is a cyclic compound containing a cycle and 2 double bonds, then the compound reduction will give a cyclic structure. But here the compound reduction gives an alkane corresponding to the formula CnH2n plus 2, which is an acyclic alkane, acyclic saturated compound it is. And therefore, it rules out the possibilities of cyclic compounds. You cannot have a cyclic substrate. You cannot have A, you cannot have B, you cannot have C. These are all cyclic compounds. So the only possibility is 3-methyl, 1-pentene for ine, 1-pentene, 1-pentene, 1-pentene means a double bond here, and 4-ine, 1, 2, 3, 4, 4-ine, 1, 2, 3, 4, 3-methyl, 1, 2, 3, 3-methyl. This is the compound CH, okay, CH, double bond CH2, and this carbon here has 4 different valencies and therefore is chiral. And once you get the saturated compound C6H14, the saturated compound will be CH3, CH2, CH3, CH2, CH3. And here these two groups become identical. That means this carbon is no longer chiral. So that's why they give you that sort of explanation. But the question can be answered even without going to the chirality aspect, because all the 3 compounds given here are cyclo. So it cannot be a cyclic compound, and therefore the only possibility is D. And therefore you can find the correct answer even thinking too much about it. But suppose you want to be convinced of all the details given in the question, then you can actually work out like this, and you will see that the starting compound is a chiral compound. It is a chiral compound. This particular compound is a chiral compound, and once you do the hydrogenation to get the saturated compound, the compound is not chiral, it's an achiral hydrocarbon of molecular weight 86, corresponding to the formula CnH2n plus 2. That means it is an alkane compound. I hope it is clear. Let us move quickly to the next question. Yes, it's a question again on conformations. Conformations, stereochemistry, optical activity, all those things together in this particular question, and the structures are given in terms of the Neumann's projections. So these are the Neumann's projections, okay? And here you find that in this Neumann's projections, suppose you very closely look at the projections. Let me discuss a little bit faster so that you will be able to complete the questions. So if you look at the structures, if you look at the Neumann's projections 1 and 2, if you tilt this 1 a little bit like this, so that the 2 CH3 come here, you will see that 1 and 2 are mirror images, which means 1 and 2 are enantiomers of this compound. The structures 1 and 2, the conformations 1 and 2 represent a pair of enantiomers of the compound. Okay, the compound is compound which exhibits optical activity because the compound is CH3 CHCl, okay, CHCl CH3. It is 2,3-dichlorobutane, and here you have a chiral carbon, and here also you have a chiral carbon. It is a compound which contains 2 chiral carbon, and the 2 chiral carbon atoms are similar chiral carbon atoms because the group substitute on the carbon atoms are similar. And for such a molecule, you know, you have a dextro compound, you have a levo compound, and you have a meso compound. You have seen 3 isomers. You have listened to the case of tartaric acid. Tartaric acid has 3 isomers. It's again a chiral molecule containing 2 chiral atoms, in which the groups attached to the carbon atoms are similar groups. Here also that is the case. For 2,3-dichlorobutane, 2 similar chiral carbon atoms, and therefore has 3 stereoisomers. One is the dextro, the other is the levo, or one is the R, one is the S, and the third is the meso. We have seen how to give RSN notations. The plus need not be R. plus, minus and meso, or it may be R, S and meso, or S, R and meso, and so on. Anyway, there are only 3 stereoisomers. So those 3 isomers are represented in terms of the Newman's projections like this, and you find that the structure 1 and the structure 2, these 2 configurations, rather than structures, these 2 configurations are enantiomeric configurations. So 1 and 2 are enantiomers. Obviously, the third one, in which all the groups are anti with respect to each other. The 2 methyl groups are diametrically opposite. The 2 chlorine atoms are again anti, and the 2 hydrogen atoms are anti, ANTI, anti. Okay? And that is the stablest conformation among these 3. This is the stablest conformation, and that represents the meso form of 2,3-dichlorobutane. So 3 is the meso form, 2 and 1 are the enantiomeric forms. Now look at the choices and which choices will be correct. 1 and 2 correspond to conformers of enantiomers. Conformers of enantiomer, that is correct. A is correct. A is correct. 1 and 2 are 2 conformers of the same enantiomer, that is wrong. 3 is most stable conformation of meso, that is meso, that is already correct. C is correct. And 1 and 3, 1 and 3, that means say the R configuration and meso, or the S configuration and meso. What is the relationship with them? They are a pair of diastereomers. Okay? So the third statement is also correct. So A is correct, C is correct, D is correct. All these 3 answers are correct. A, C, D. That's the correct option for this. And the wrong statement is 1 and 2 are conformers of the same enantiomer of 2,3-dichlorobutane. 1 and 2 are actually conformers of the enantiomers. Conformers of the enantiomers. Okay? That means these 2 are different compounds. All the 3 are different compounds. They are enantiomers, and this are diastereomers. This and this are diastereomers. 1 and 3 are diastereomers. 2 and 3 are diastereomers. 1 and 2 are enantiomers. So that is the thing that you know, or you want to know. We have already said about tartaric acid. Now is another good example. It is 2,3-dichlorobutane. I think with these examples, the absolute configuration, how to write the absolute configuration, how to decide the Newman projections, and how to decide the stereochemistry in total about these molecules. I think you are clear about it, and questions of that type can be easily answered once you know details like this. Okay. Now, question 17. Which of the following carbocations undergo favorable rearrangement to more stable? Actually, it must be R here. More stable one. Symbol structures are given. So think about the possibility of carbocation rearrangement. And remember that rearrangement is different from resonance. In a rearrangement, there will be migration of atom or group from one position to another. Then only you can call it a case of rearrangement. So for example, in carbocation chemistry, a rearrangement means a hydride shift or a methyl shift. Then only you can say there is rearrangement. If it is just a pi electron delocalization, it is resonance. So you have to differentiate between the 2 things, resonance and rearrangement, while you discuss this question. So in the case of the first one, see in the first one, okay, this is the first compound. Remember that there is a hydrogen here. Here is a positive charge. Here there is a hydrogen atom. So it is a carbocation, and the hydrogen can be shifted to this, in which case you will have the structure, okay, the hydrogen is shifted to this position, means the positive charge is now here. So this is a rearrangement. This is a rearrangement, and here the positive charge is on a carbon which is already attached to 3 other atoms. It is almost like a tertiary carbon. Of course, to 2 carbon and 2 oxygen. but still attached to 3 atoms other than hydrogen. So it is well and good, equivalent to a tertiary. And here on the oxygen you have lone pairs. The lone pair may be shifted like this, so that a double bond comes here and the positive charge is on oxygen. You can have this structure, okay, double bond, OH positive. But this part of the representation is only a case of resonance, and this part is a case of rearrangement. And because of resonance, this is stabilized, and therefore you can say that A is a structure which undergoes a favorable rearrangement so as to give a more stable carbocation. The more stability is due to the resonance of this, resonance stabilization of this. So there is a rearrangement because there is hydrogen migration. Okay. Now what about structure B? So A is a correct answer. Now what about the structure B? It's a simple question. So already you have a positive charge on a tertiary carbon. And normally we think that the tertiary carbon is stable, more stable than secondary, more stable than primary. That is the usual statement that we study by heart, isn't it? All of you have it in your mind. But there are certain situations in which a secondary carbocation may become even more stable than a tertiary carbocation if the additional stabilizing factor is there. So whenever you apply the concept that tertiary is greater than secondary, greater than primary with regard to stability, it is very important that no other stabilizing factor is there in that particular molecule. Now here look at this structure. Suppose a hydrogen from here is migrating to this position. You can have a hydrogen here, and here you have the positive charge. And here you have the lone pairs on the oxygen, and this lone pair again can be shifted here so that you have a double bond here, and thereby this can be resonance stabilized. Obviously, this is a tertiary carbocation, but during rearrangement by the hydrogen shift, you are getting a secondary carbonium ion which you may think is less stable, but it is more stable because of the resonance. That's the point. So there is a chance that this tertiary carbocation here can have a hydride shift, a 1,2 hydride shift. The hydrogen from here can shift to this position so that a positive charge is here. So this is the carbocation, and this carbocation has the additional stabilization due to resonance. These lone pairs will come here so that you will be able to write the resonance structure. Okay, a double bond OH positive. So this part I tell you is again resonance stabilization, whereas conversion of this to this is a case of rearrangement. So B also is an answer because B can rearrange to a carbocation which is stabilized by resonance. That's the point, even though it is tertiary to secondary. So there are certain situations when a secondary may be even stabler than a tertiary, provided the secondary has additional stabilizing factors. Additional stabilizing factors. Here the additional stabilizing factor is resonance stabilization. Here there is no resonance stabilization. Here there is resonance. So that is. So what about this C? C, once you see C like this, okay, here also you can put this delocalization of the pi bond so that the positive charge is neutralized here, and you have the positive charge now. The positive charge delocalized, okay, and the positive charge comes here. But it is just a delocalization of pi electrons. Delocalization of pi electrons is what you call resonance, and there is no shift of a hydrogen atom or methyl group here. So this change cannot be called as a case of rearrangement of carbocation. There is no rearrangement because there is no hydrogen migration. There is no methyl migration. There are two types of migrations. one is a 1,2 hydrogen shift or the other is a 1,2 methyl shift. Nothing happens here except pi electron delocalization. So there is stabilization, but there is no rearrangement. And in this case also, you can have stabilization because the positive charge is in conjugation with the pi bond. So you can have, in this molecule also you can have, okay, in this molecule also you can have the pi electron shift like this, so that the double bond is here and the positive charge is here. The double bond is here and the positive charge is here. That is possible, but however, here also you find there is only pi electron delocalization and there is no shift of a hydrogen atom or a methyl group as is there in all carbocation rearrangements. So this cannot be called as a case of rearrangement. This cannot be called as a case of rearrangement. This can only be called as cases of resonance stabilization, whereas in the first and second example, you have hydrogen migration. That means you have rearrangement of carbocation and the resulting cation stabilized by resonance. Therefore, it is favorable because a more stable species is formed and therefore it is favorable rearrangement. So what is the correct answer? The correct answer is A and B. A and B are the correct answers to this particular question. It's a good question. Though not very difficult, it's a good question. Yes, now this is pretty simple question. 18, in which of the following reaction the Kolb's electrolysis, and the conventional Kolb electrolysis in your mind is the electrolysis of potassium acetate or sodium acetate, in which two molecules of, you formulate the reaction like this, you get ethane plus 2 carbon dioxide plus 2 KOH plus H2. These are the electrolysis products. So what you find is that the decarboxylation is there on this part of the molecule and the methyl groups are joined to form ethane as a product. This is the classical example, the first example that you study in Kolb's electrolysis in your 11th standard relating to the preparation of alkanes on a limited scale. So preparation of ethane by the Kolb's electrolysis of potassium acetate. Now when you apply the same idea of Kolb's electrolysis to these molecules, what will be the product? What will be the product? The first case, what is the product? Okay, the 2 carbon dioxide are detached and you have a bond created between the carbon atoms which were holding the COH groups. You have a double bond between the carbon atoms which are holding the double bond. Okay, so this is correct. A is correct. Now what about B? B is the compound. You have CH2, this is COK, CH2, COK, CH2, this is a compound. And again, the 2 CO2 detached, decarboxylation during electrolysis, and a bond is created between these two. And therefore, you get CH2, 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 and that is the correct one here. So B is also correct. Now what about C? Here you find this is the compound COK, and here there is a CH2 group. Don't forget that, COK. So the 2 carboxyl groups are detached and a bond is created between the carbon atoms which were holding the carboxyl groups. You have to think like that. So a double bond is appearing here. So the product actually obtained would be this product. In C, the product obtained would be this one and not this. So the answer C is not correct. This is not the correct match. And what about D? D is similar to this one. You have 2 molecules here, CH3, CH2, CH3COK, okay? And you have CH3, CH2, CH3COK. So 2 molecules detached and a bond is created between these carbon atoms, and that's the product given here. It is this product, CH3, CH2, CH3, CH3, CH2, CH3. It is given as bond line representation, but what is formed is this particular molecule. So the option D is also correct. So the only mismatch is option C, and that's the answer to the question. The incorrectly matched is C. And I think this particular question was also asked in a previous JEE main examination. This question is from a previous question paper. It seems that's my okay. The next question. What is a major bromination product in the following reactions? And here you have 2-butene. What is a major bromination product? Remember, the bromination reaction is again photochemical here. So we have seen at least 3 examples where you have photochemical chlorination or photochemical bromination. Here is a photochemical reaction. That means you have a radical CH2, this radical, and the bromine radical. But what happens is the bromine radical immediately doesn't bind here, because this molecule has a structure in which the unpaired electron is in conjugation with the double bond. So I can the double bond shift like this to give CH3, CH double bond CH2, so that the unpaired electron now comes to this carbon atom. And this is advantageous. Why? This is a primary free radical, whereas what you get by the pi electron shift is a secondary free radical. And the secondary free radical, we have already said, is more stable than the primary free radical. Okay? In both cases, there is conjugation. The electron and the double bond in conjugation. Here also the electron and the double bond is conjugation. But here it is a primary free radical, whereas in this case it is a secondary free radical. And obviously, this free radical initially formed will be converted into the secondary free radical, and this secondary free radical now takes the bromine, and you have CH3, CHBr, CH double bond, CH2. Okay? So that's a very simple question. I think all of you will get the answer. What is the answer? CH3, CHBr, CH double bond, CH2. The correct option is C. From the options given, the correct option is C. Okay? Yes. Now coming to question number 20. What is a major product of the reaction below? Look at the question carefully. Look at the question very carefully. It's a diphenyl system, and you have bromine atom on one phenyl ring. And we know that the bromine atom is usually slightly deactivating sort of atom because of the electronegativity. It reduces the electron density in this benzene ring, which means the electron density in the other benzene ring is not reduced. So naturally, the electrophilic substitution will preferentially take place in the second ring, which is not disturbed at all. There is no group there deactivating it, but here is a bromine atom deactivating it. So this benzene ring, which is not deactivated, will be the ring in which the nitration reaction takes place, and the nitration will preferentially take place at the para position, because the ortho positions have steric hindrance, and moreover has the electron displacement effect from the para bromophenyl group. So the comfortable position in which the electrophilic substitution can take place is the para-nitro product, that is para-nitro compound, that is the option D. D is the correct option. D is the correct option. Shall we go for some 15 more minutes? Okay. If you have 15 more minutes, I think I can quickly. If you, audience, are patient enough to listen to me for a few more minutes, I think in the next 10 minutes, I can quickly answer the single digit answer questions, because they are rather very simple. The number of cyclic isomers of the ether. This is a question which has been asked for many question papers, and I think this example might have been taught in all the classes. It is C4H8O, means this is the compound, C4H8O, and you can have the other isomers like this you can have this, and then you can have, okay, 3, you can have this, and you can have this. And since here is a hydrogen atom, this becomes chiral, and therefore it has R and S configuration. And here, this carbon atom has hydrogen atom, here it is chiral, and this carbon atom also chiral. That means this can have the R form, you can have the S form, and it can also have the meso form. Do you follow? And therefore you have 3 plus 4 plus 5 plus 3, 8, and you can have one more compound, isn't it? You can have an ethyl group. That is another possibility. You can have that possibility also. So you have this compound. Again, you have hydrogen atom here, and here it is oxygen, here is a carbon. That means this carbon is chiral, and this also has the R configuration and S configuration. Therefore 1 plus 2, 3, 4, 5 plus 3, 8 plus 2, 10. You have total 10 isomeric cyclic ethers of this particular formula. That's a very, very good question which has been asked many times. You can very easily follow the question. Again, the next question is about the number of monochloride derivatives. Perhaps a repetitive sort of question, including stereoisomers of 2-methylpentane. This is 2-methylpentane. Reaction with 1 mole chlorine. If the chlorine is substituted here, there is no stereochemistry and you get only one compound. But if the chlorine is substituted here, then also at this carbon, if the chlorine is substituted here, okay, if the chlorine is substituted here, then also these 2 methyl groups are same, and therefore when the chlorine is substituted here, you have only one compound. But when the chlorine is substituted here, actually, in the first case, it becomes a CH2Cl group, so that this carbon becomes chiral. It's a hydrogen here, a methyl here, a chloromethyl here, and a propyl here. So this carbon will become chiral, and therefore you will have 2 isomers when a chlorine is substituted on this methyl group. When a chlorine is substituted here, you will have only one isomer. But when a chlorine is substituted here, again, remember, this becomes, how many? This becomes, you have chiral, and therefore you have 2 isomers. When a hydrogen is substituted by chlorine here, then also you have 2 isomers here. And when a hydrogen is substituted here, you have only one isomer. So 1 plus 2, 3, plus 2, 5, plus 1, 6, plus 2, 8. You have a total of 8 isomeric compounds. Now this is something which we have already discussed in connection with the previous topics. When one chlorine comes, look at the possibilities, and in which all possibilities you have chiral carbon atom, and decide the number of chiral isomers also. So the total number of compounds obtained is the total number of isomers, and when you count the total number of isomers, you have to take the structural isomers as well as the stereoisomers. Remember that. In an estimation bromine by Carrier's method, this the simplest of the questions. 1.6 gram of an organic compound gives silver bromide. That's a question from the estimation part of in the first chapter. Estimation of organic, the elements in the organic compounds, the quantitative analysis of organic compounds. And here it is a question about bromine, which is converted into silver bromide. You are getting 1.88. So it has to be multiplied by a factor which is equal to the atomic number of bromine, atomic mass of bromine, that is 80, divided by the molecular mass of silver bromide, AgBr. The molecular mass is 108 plus 80, that is 188. For silver bromide, bromine atomic mass is 80. So the mass of bromine in this much of silver bromide will be 1.88 into 80 by 188. So that divided by the mass of the compound 1.6 into 100, okay, will be equal to the percentage of bromine, and this will work out to be 50%. You can do that. It is very simple. 1 second calculation, 50%. That's the answer. So very simple question, very straightforward, very direct question it is. And now question 24. How many of these are aromatic compounds? I think students who study aromaticity, the conditions are cyclic, planar, conjugated, and contain 4n plus 2 pi electron. These are the 4 conditions to be satisfied for a structure to become aromatic, where En is equal to 0, 1, 2, 3, etc. So you check whether the structures are cyclic, structures are planar, structures are conjugated, and structures containing 4n plus 2 pi electrons. And all these examples are usually examples taught in the class. This is just a question based on classroom discussion. This is cyclooctatetraene. Of course, it is conjugated, but it is not planar. It is cyclic, conjugated, and it doesn't contain 4n plus 2 pi electron. And therefore, the first one is not aromatic. The first one is not aromatic. What about the second one? The second one is cyclic. It is planar. It contains just 2 pi electrons and the positive charge, which are conjugated. Okay? And then you have only 2 electrons, which corresponds to the formula n equal to 0. So it is conjugated. It is planar, it is cyclic, it contains 2 pi electrons corresponding to the formula for n plus 2. And therefore it is aromatic. Cyclopropenyl cation, that is aromatic. And the next is the cyclopentadienyl anion, that also contains 6 pi electrons. It is cyclic, it is planar, it is conjugated. So third one is also aromatic. The fourth one, of course, may look planar. It is not actually planar. Why? Because there is no double bond here. So it is not fully conjugated, even though cyclic. And it is not still planar and doesn't contain 4n plus 2. It is not aromatic. Then this compound is now quite known to you. It is naphthalene. And naphthalene is obviously following all these criteria and therefore is aromatic. And this one is the compound what you call azulene. Azulene is isomeric with naphthalene. It has a 7-membered ring and a 5-membered ring. But the 7-membered ring has positive charge, means the 4n plus 2 rule is satisfied, and the cyclopentane ring has a negative charge, which means that also follows the 4n plus 2 rule. It has in total 10 pi electrons, as is the case with the naphthalene. It is cyclic, it is planar, it is conjugated, it is aromatic. Azulene is aromatic. And this is pyridine, which is very similar to benzene. Only thing is that one position is occupied by nitrogen. It is cyclic, it is planar, it is conjugated, it contains 6 pi electrons corresponding to the formula 4n plus 2, and therefore that also is aromatic. And out of these 7 structures, you have 4 structures which are aromatic. Now is the last question, which is a very simple problem in relating to empirical formula and molecular formula, but asked in a different way. The percentages are not given, but the ratios are directly given. You have carbon and hydrogen in the ratio 4:1, and you have carbon and oxygen in the ratio 3:4. Okay? Carbon and hydrogen and carbon and oxygen of a saturated acyclic compound X are 4:1, carbon and hydrogen 4:1, and carbon and oxygen 3:4. And you make it 3. Carbon is 4 here and carbon is 3 here. Okay? So if you make the carbon the same, it will be 12:3 here and it will be 12:16 here. So that the ratio of carbon, hydrogen and oxygen is the mass percentage ratio. It is a mass percentage ratio 12:3:16. So that the mole ratio will be the mass divided by atomic mass. It's 12 by 12, 3 by 12, 16 by 16. 3 by 1. Atomic mass of hydrogen is 1. Atomic mass of carbon is 12. So 12 by 12 is 1. 3 by 1 is 3. And 16 by 16 is 1. So that the empirical formula of the compound will be CH3O. That's the empirical formula. Then the question is, then the number of moles of oxygen gas required for complete combustion of 2 moles of the organic compound X. The empirical formula is the only formula that is known now. So what will be the formula of the compound? The molecular formula of the compound. What will be the molecular formula of the compound? It is given that the molecular mass of the compound, actually you must have a knowledge about the molecular mass of the compound. The empirical formula of the compound is CH3O. You cannot write a molecule like the known molecule is CH3OH, which is CH4O. You cannot have a molecule CH3O with a molecular formula CH3O. It can have an empirical formula. So at the minimum, that's the point, at the minimum, the compound must be T2H6O, which will correspond to the molecule CH3O, OCH3, that is dimethyl peroxide. You cannot have a molecule CH3O as a stable neutral molecule. You cannot have. Whatever compound that you know is CH3OH. You have another compound HCHO, formaldehyde, but that is only CH2O, it is not CH3O, which means you cannot have the molecular formula CH3O, it must be at least C2H6O, and there is a compound corresponding to the formula CH3OOCH3. So this compound fits all the data given in the problem. So the compound is this one, and this compound C2H6O, okay, C2H6O. When it combines with oxygen, C2H6O combines with oxygen, you have 2 carbon dioxide and 3 H2. And what's the question? What is the number of moles of oxygen required for complete combustion of 2 moles of the organic compound? You simplify this, you balance it. So 2 carbon dioxide, 6 hydrogen means 3 H2O. You require 2 into 2, 4 plus 3, 7 oxygen atoms. Already 1 oxygen atom is here, and therefore you require 3 oxygen atoms, okay, plus 3 O2, isn't it? C2H6O2, here C2H6O2, that means you require only 2 and, okay, 2 and a half. It is 4 oxygen here, 3 oxygen here, 7, 2 oxygen here, 9, okay. So you require only, here 3 plus 4, 7, and here already 2, that means you require only 2 and a half O2. That means for 1 mole of the compound, you require 2 and a half moles of O2. For 1 mole compound, you require 2 and a half moles O2. So the question is, what is the number of moles of oxygen required for complete combustion of 2 moles of the compound? If you have 2 moles of the compound, you will require 5 moles of O2. 5 moles of O2. So that's the answer. So you require 5 moles of O2. Then the number of moles of oxygen required is 5 moles of O2. It's a question, very simple arithmetic. Maybe called as a question belonging to the first chapter, basic chemistry, or it is a question equally applicable to calculation of empirical formula, molecular formula of organic compounds. So that is why the question is justifiable in this section as a single digit answer question. So it's very simple, easily solved. You find the CH ratio, CO ratio, then find CHO mass percentage ratio divided by the atomic mass, get the mole ratio, write the empirical formula, see whether there is any molecular formula corresponding to this. You don't find any molecular formula, but for the dimer of this C2H6O, you have a molecular formula CH3O, CH3. That's the simplest possibility. And if this compound C2H6O burns in oxygen, the amount of oxygen required is 2.5 O2, and therefore for combustion of 2 moles, you require 5 moles of oxygen. Okay, so with this, of course, towards the end we have to rush to finish the questions now that it is more than 12 minutes extra we have discussed, but however we could complete all the questions. So there are some good questions among the 25 questions, at least some 10 to 15 questions are quite good questions, and the remaining questions, there are 4 or 5 or 6 simple questions, and you do weightage to these questions and prepare all the best, and on the whole you find there is a lot of stereochemistry involved in various questions. So study that very well so that you are assured of answering stereochemistry questions, and you are also carbocation mechanisms, rearrangements and all that Those things also you actually take into consideration. And these are some questions relating to aromaticity, and more important about the number of isomers corresponding to a formula. And also you have a question where you have to distinguish between rearrangement and resonance. In resonance, there is no rearrangement, there is only pi electron delocalization. Whereas in carbocation rearrangement, remember there is migration, or in any rearrangement for that matter, there is migration of an atom from one position to another. Then only you can call it rearrangement. So the carbocation rearrangement is a rearrangement, and in the rearrangement we found that compounds are stabilized by resonance. So there are both there, and that's why favorable rearrangement. But in the latter two examples we have seen that there is no rearrangement, there is no migration of hydrogen atom or methyl group. There is only delocalization of pi electrons. So that is only a case of resonance. So you have to differentiate that to answer that particular question. I think the discussion can be wound up now, and thank you for patient listening. Goodbye. Can you